All right, welcome back. Dr. Pitcher here, and we'll continue with lecture videos for Chapter 3, Alkanes. And in this lecture video, I'm going to go over conformations of straight-chain alkanes. Specifically, we'll look at conformations of ethane, propane, and butane. So let's start with the conformations of ethane. Before I do that, let me just give a definition. And a conformation is simply a snapshot of a three-dimensional structure. That is, it's a glimpse of what the molecule looks like at a brief moment in time. Okay, so in reality we have a molecule like, let's say, ethane, that is spinning around, tumbling around, and at one particular moment in time it has a particular conformation. That's its actual three-dimensional structure. So we could, if we build our model of ethane, we could draw some different versions of this. So let's start by drawing, maybe we'll draw this. I'm going to draw this version like that. There we go. So I could have carbon bonded to a carbon. Up here I have a hydrogen. Down here I have a hydrogen. And then I can use my wedges and dashes to represent the other hydrogens. And so what we're doing is we're actually taking a look at it like so. Okay, I've got hydrogen, carbon, carbon, hydrogen. Those have the lines there. They're all in the same plane. And I've got hydrogens pointing out towards us. Those are the wedges, and hydrogens pointing away from us. Those are the dashes. Okay, so if I want to, I can actually represent this in different ways. So this is my three-dimensional, or my representation of the three-dimensional structure on a two-dimensional piece of paper. I could have a model, and I can play around with the model. So let's take this structure, and I'm going to actually look down one end of the model. So what I'm going to do is I'm going to take my eyeball here, and here is my eyeball. Give it some eyelashes. And I'm going to sight down this carbon-carbon bond axis. Okay, so what is that going to look like? Well, let's take a look here. Let me move this guy out of the way. And so I've taken this, and I'm just looking down that carbon-carbon bond axis, and this is what I'm going to see, looking down there. So that is what I see. So it looks like I've got my front carbon, and I've got three things, and it looks like they're separated by 120 degrees. Now, of course, in reality, the bond angle is 109.5, but because we're looking at it from one end, it looks more triangular. So I can draw this. And I'm going to draw it using something called a Newman projection, which you guys encountered in lab. So let me start off here. So here is my initial Newman projection. And this carbon, you can see if it's not straight on, if it's straight on like that, there we go. That's what I'm trying to capture with my drawing. Here, maybe I'll do that so you guys can see it a little bit better here. Okay, now it's hard for me to show the back carbon because it's right behind the front carbon. So what I'm going to do is draw a circle. And then I'll show where the other hydrogens are coming off of that back carbon. So let me just label these here. So I have my front carbon and my back carbon. So I figure I'll go over this in a little bit more detail than we did in the in class, because that was just kind of quick and helping you guys be able to do the lab. So this is a Newman projection, and in this particular conformation we call this staggered. And in the staggered conformation, I have a bond angle here, not a bond angle, an angle here, theta, which equals 60 degrees. Okay, and I can see that. I've got my gray bonds here. Let me put it on the dark background, a little easier to see. A bond there, my other bond there, and the angle between those is 60 degrees. So that's 60 there, 60, 60, etc. All adds up to 360 degrees. We call theta the dihedral angle. Let me write that down here. So theta equals dihedral angle. And it is literally what it is describing. The dihedral angle is the angle between the bond in the front and the bond in the back as you're looking at it from one end. So I could rotate my back carbon here 60 degrees. So I hold my front carbon in place and I rotate the back 60 degrees. Now everything lines up. So I could draw that conformation. So rotate back C 60 degrees. Now, it's hard because all of my hydrogens are overlapping with each other, or they're in front of each other. So what I'm going to do is I'll just draw my line for the back hydrogen alongside the line for the front hydrogen. We call this the eclipsed conformation. And now you can see here that my dihedral angle, theta, equals 0 degrees. And this is really the way that we want to label things. We have a dihedral angle, and so we've got 0, there we go, let's do this, 0, 60, 120, 180, 240, 300, and then back to 360. So this is slightly different than what's mentioned in the modeling lab. There you had a staggered conformation that was called 0, but I think it makes more sense to let the degrees refer to the actual dihedral angle. So if we want to, we could make an energy plot of this. Now first of all, let's take a look energy-wise at what's going on here. And I'll leave that up there if you guys want to, you can go ahead and pause and jot down these notes. All right, now that you've unpaused, let's see what our energies might look like. So here is my eclipsed, and we know that's the highest energy. Why? Well, these hydrogens are a little closer to each other, but it turns out hydrogens are small. So in reality what it is it's these electrons. Let me get a different model. I'll be right back. Here's another model of ethane, but this is showing orbitals. These kind of grayish things here are the orbitals, the sigma bonds. Okay, and these are actually sizable. And so what we have when we have eclipsed is it's actually, in the case of hydrogen here, we have a repulsion between the electrons in the orbitals, and that gives rise to the energy difference between staggered and eclipsed. We call that a torsional strain. So let's call this energy differences in alkane conformations. So our torsional strain is due to the orbitals. Okay, so this is from the orbitals. So strain due to we'll say electrons in bonds. Yeah. There are some nuances to it. The text actually refers to, you know, I've got it right here. It's the cause of torsional strain has been the subject of controversy, but the major factor is an interaction between CH bonding orbitals on one carbon and anti-bonding orbitals on the adjacent carbon. Actually, what it's saying is that this is more stable because the bonding orbital here interacts with the anti-bonding orbital here. That's a little hard to get your head around, I think, because anti-bonding orbitals are not necessarily intuitive. I just like to think of it as, you know, okay, it's an effect from the electrons, the orbitals, but lining them up is bad, staggered is good. And torsional strain is what's going to cause our different dihedral angles to have different energies. Now, we could have another type of strain, which we'll see later, and that's called steric strain. And that's due to atoms being close to each other. Now, it's not a very big effect for hydrogen, so the steric strain here is not that big. I mean, that relieves any steric strain. But if we have big groups, we can get quite a bit of steric strain. And we'll take a look at that when we look at butane. And later when we actually look at some cyclohexane derivatives. All right. So let me put away my orbital model here. Hold on. Let's take a look then, and we'll go ahead and make a plot. And I'm going to have to make a plot here. And we'll put energy on the y-axis and theta in degrees on the x-axis. So we'll start at 0, and we'll go 60. 120, 180, 240, 300, and then 360 brings me back to where we started. Okay, so I'll just kind of, I'll put it right there, right in the middle. Here we go. So 0 is like this, totally eclipsed. And that's going to have some energy. And then when it's staggered, we've removed all of that eclipsed interactions. So we're going to call that 0. And then if I rotate, I'm now at 120, but I'm eclipsed again. So I go back to that same, let me try to actually draw this in the right place here. Go back to that same point. 180 will be 0. 240. Now I'm rotating the front carbon. You can rotate either one. It's just a little easier for me to do here. 240 is again back at that high energy. 300 is at 0, and then 360. So my angle is 360 all the way around. I'm back to where I started, and that is at that energy. Now we can have intermediate angles here. So, it's not necessarily the case that we're stuck to 0 and 60. We could have like 45. We call those conformations skew. So skew is in between staggered and eclipsed. All right. Now, what are the actual energies? So we can get our actual energy values. Can get energy values. And we can get them actually from a table in the text, which is table 3.5. And so what table 3.5 tells me is that my hydrogen-hydrogen eclipsed, which is due to torsional strain, has an energy cost of 4 kilojoules per mole. So 4 kilojoules per mole. But that's for each hydrogen-hydrogen eclipsed. So I have 1, 2, 3. So that would be a total of 12. Kilojoules per mole. And then of course I'm at 0 down here. And so if you're making a plot like this, you can connect them with a smooth curve, a reasonably smooth curve. Kind of looks like a sine wave. There we go. And now this is, there we go. Now this is going to look a little different than what you graphed in the modeling lab, which is essentially just shifted over, or maybe it's shifted that way. Anyway, it's shifted over by 60 degrees, where your peaks and valleys are. All right. So that's our energy picture of the different energies for ethane. So in reality, the molecule is spinning around, and this 12 kilojoule per mole energy difference is not really that big. So it doesn't take a lot of energy to get this one end of the methyl group to be rotating around. Most molecules, you can consider the methyl groups to be just kind of freely spinning like little propellers or something. And especially on longer time scales, you're going to see, these guys averaging just any of the conformations, but more time in the staggered than in the eclipsed. Now, when we get to bigger groups, we'll see that the energy barrier gets larger, and we'll see that some conformations are much more stable, and so they'll be the more important conformations when we're looking at how things react. All right, so let's take a look at, and again, this is ethane. Let's take a look at propane next. And I'll go ahead and take a hydrogen off and put a methyl group on. And here is my propane. So I'm going to hold it like this. And hopefully you guys can see that. I know my white background is not the best for having the white hydrogens here. So I've got a methyl group here. Now, if I wanted to go, let's just say I wanted to be totally staggered, I would have something that was like this, actually. This is, you can see where we get our zigzag from when we draw our bond line structures for alkanes. And if I look down this bond axis, everything is staggered. If I look down the other bond axis, everything is staggered. But for the purposes of the Newman projections, I'm going to ignore what's going on with one of the methyl groups. I'm just going to say this is CH3. It's something that's just doing its own thing. It's this big thing there. And then I'll go ahead and let me orient it like that. There we go. So I've got carbon in the front, and then hydrogen, hydrogen, and I've got CH3. So if I draw this guy here, so this is my eclipsed, HHCH3. Here's my back carbon, and in the back I've got a hydrogen. Let me scoot that down. There we go. Hydrogen, that's eclipsed by the methyl. You can see there, methyl, hydrogen. So I'll go ahead and put that there, hydrogen in there. And I have a hydrogen eclipse there and a hydrogen eclipse there. And that's theta equals 0 degrees. And then if I rotate, so let's go ahead and rotate, I'll rotate the back carbon this time. Again, now I've got CH3, oops, this guy's going to fall over. Do that, there we go. So now I've got my staggered conformation, so let me draw that. And I just knocked it over, sorry about that. Now you will want to practice drawing oops, not 6 degrees, 60 degrees. You will want to practice drawing, not staggered, hold on, staggered. You will want to practice drawing Newman projections, both eclipsed and staggered conformations. So again, here's my theta equals 60 degrees right here. So you will want to practice drawing these Newman projections. You'll have to do it on the quiz and on the exam. Now, this energy plot actually ends up having the same shape. As the energy diagram for ethane. So I'm not going to draw it quite as big. I'm not going to go all the way to 360. But we'll have our eclipsed, staggered, so higher energy, lower energy, we're going to call it 0, and then eclipsed again, and then staggered again, and then eclipsed again, and then staggered again. So it's going to have the same basic shape, I'll go ahead and put 360 in here, why not? So I can go ahead and connect these guys with smooth curves, more or less. Depending on your artistic ability, your mileage may vary. Only now, if I look at table 3.5, I can see that a hydrogen methyl eclipsed, which is mostly torsional strain, but a little bit of steric strain, is 6 kilojoules per mole. So in each case, I have HH, HH. So I have 2 hydrogen eclipsed. So that's 2 times 4, 8. And then I've got another hydrogen methyl eclipsed, which is another 6. So this would be 14 kilojoules per mole total. All right. Now, there are actually illustrations of these diagrams in the text, so I recommend looking at them. They're a little prettier than mine. So, you know, if you're going to be referring to table 3.5, you might as well look at figures 3.8 and 3.9 and figure 3.9 seems to have disappeared from my that's interesting. The text does not have a figure 3.9. I think it was supposed to, and it disappeared during editing. Interesting. Figure 3.8 is the conformation of ethane, the energies of that conformation. So it was this guy's figure 3.8. And then figure 3.10 is butane. But this, figure 3.9, does not actually appear to be in here. Oh, there is a figure 3.9, but it doesn't show the actual energies. All right, I do apologize. Okay. Anyway, I'd like to refer to figures because in the text, because a lot of times the text draws things a bit better looking than I do. All right, let's look at our last case here, and that is butane. And so what I'm going to do is I'm going to let's see, let's draw our graph here, and I'll see if I can squeeze in all of these conformations. So here's my energy in kilojoules per mole, and this is going to be theta in degrees, starting at 0, 0. All right, so let me pull a hydrogen off my back carbon here, and boom, butane. Again, the most stable conformation is going to be this one, is completely staggered. But in reality, the butane molecule is kind of twisting and tumbling around when it's floating around in butane's a gas at room temperature and pressure. Yeah, it's just kind of floating and tumbling like this. But if we freeze it, we'll see that I mean, not really freeze it, but just take a snapshot of it. Look at the conformation. We'll see that the totally staggered is the lowest energy. So boom, 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 boom. So let's start actually with the highest. Well, we'll start with the lowest energy. I'm going to put it in the middle here. And let's see, that's 0. So let's do 60, 120, 180, 240, 300, and 360. So when theta equals 180 degrees, so my theta is going to be my bond, or my angle between this bond and this bond, my 2 methyl groups. So I'm looking down the middle carbon-carbon bond. Okay, this would be 0, 60, 120, 180. All right, so I've got my C. Let's see, where should I? Yeah, that's actually fine to do over there, I think. Sorry, I've got C, C, CH3, CH3, H, my wedges and dashes here. and I will, get my eyeball, and I'll go ahead and I'll look. Where's my eyeball? Go to my eyelashes. There we go. I'll look along that carbon-carbon, the C2C3, because 1, 2, 3, 4, C2C3 bond. So if I'm totally staggered, that's going to be 0 energy. All right. Just make sure you guys can see that. Sorry, I may have been drawing that off camera here, but I'm looking down my carbon 2, carbon 3 bond. 1, 2, 3, 4, so 2, 3. There's my eye looking down that bond. And then I can draw that here as H, CH3, CH3, H. This is theta equals 180 degrees. It is one of the staggered conformations. In particular, it's called the anti-conformation. All right, these two methyl groups are opposite to each other. If we drew an imaginary line here, there are imaginary plane here, they're on opposite sides. So we say they're anti to each other. If they're on the same side, they'd be syn to each other. That would be our terminology. These are anti to each other. So this is 180. And that's our lowest energy. Now our highest energy is where we have something totally eclipsed. So my methyl groups are eclipsed, and you can even, you can hear that. My methyls are bumping into each other. When bits of your model make noise bumping into other bits of your model, that's an indication that you have steric strain. All right, so this is an example of steric strain. These methyl groups are relatively large compared to the hydrogens, so there is a physical repulsion between them. So at 0 degrees for our dihedral angle, it's going to look something like this. So maybe I'll draw it down here. Let me put it on screen. Sorry about that. CH3. A little hard to see some of these guys here. So this is theta equals 0 degrees, totally eclipsed. Now, what's the energy? Well, I have 2 hydrogen-hydrogen eclipsed interactions. So each of those is 4, so that's 8 total. And then I have a methyl-methyl eclipsed interaction. And looking at my chart, that's 11. So 8 and 11 gives me a total of 19 kilojoules. So 10 is going to be around there. All right, I'm just trying to figure out exactly where my plots are. All right, so let's go ahead. I'm gonna rotate this front guy here, and let me line that up. So there we go. So now I've got my staggered conformation with theta equals 60 degrees. So let me draw that. So in the front, I have, let's see here, H, boom, boom, CH3, H. And then in the back, I have CH3, H, H. Now this is staggered, but it's not as low in energy as the anti-conformation, because the methyl groups still are not, I mean, if I kind of, let me hold this in place, I could kind of bend it and make them bump into each other. It is just a model after all, but there is some repulsion there. And the term that we use for that, the terminology we use for that is gauche, G-A-U-C-H-E. It's a French term, and so gauche refers to that repulsion. It's not as big as any of the eclipsed interactions. If I look at my table, I see that gauche, which is a combination of torsional and steric strain, is just steric strain. The eclipsed, methyl eclipsed was torsional and steric. Gauche is just steric strain, is 3.8 kilojoules per mole. So that's going to be, if that's 10, then 3.8 is about there. And then I'll go to my next eclipsed conformation. Let me draw this down here. So this is theta equals 60 degrees. And it's gauche. What did I do? Oh, I messed that up. Sorry. Let's draw it down here. I'm going to have to draw it over here, actually. So I've got H, and in the back I have CH3. I have CH3 there, H there. I have H and H. So this is my theta equals 120 degrees. And that's also eclipse, but now I've got two methyl hydrogen, and those were 6 kilojoules per mole. So 6 and 6 is 12, and then hydrogen, so that's another 4, so that's 16. So I'm not quite up to the high point. There we go, so maybe about there. So I can start connecting these if I want. Now if I keep going, and I won't draw these, actually in figure 3.10 all of them are shown, and you may have to zoom in on it if you're looking at your the PDF version. But you know, so here, this is my 120. Let me start over here. 0, 60, 120, 180, 240. It kind of looks like the 120. I've got the same interactions. 1 hydrogen-hydrogen eclipsed and 2 methyl hydrogen eclipsed. So 240 is going to be back at that point. And then 300 is another gauche interaction, so that's there. And then 360, I'm back to where I started. And again, I could connect these with smooth, oh, that was not very smooth, Wayne. Smooth curves here. Sorry about that. Whew. Yes, again, the, let's try to make that a little better. There we go. The picture in the text, in fact, I've got it right here. So why don't I just show you guys, and you can look at this. This is a prettier version. But the 0 here is in the middle. 0 degrees is in the middle. So in my case, 0 is at the one end. All right? But, yeah, you're going from highest to lower, but not the lowest, to high, but not the highest, and then to the lowest, and so on. Okay, 0 degrees, torsional angle, or dihedral angle, sorry. That is totally eclipsed. 60 degrees is gauche. 120 degrees is eclipsed. 180 degrees is staggered, or sorry, is anti-staggered. Gauche is also staggered, but this is anti. And then 240 is eclipsed. 300 is gauche, and 360 is back to where we started with totally eclipsed. All right, so those are conformations of a few molecules. And if you wanted to look at conformations of other alkanes, you just have to figure out which bond to look down. So let's say, for example, we wanted to look at 2-methyl butane. So 2-methyl butane has the following structures. There's my butane, and there's going to be a methyl group on carbon 2 here. So I'm going to add in CH3 just so we keep everything straight here. So you'd pick a carbon to look along. So maybe we'll look along this carbon here, and we'll go ahead and take my eyeball, and we'll look along the C2, C3 axis. And you then figure out what your Newman projection would look like based on how you're looking at it. So I'm looking down here, I'm going to have a CH3 on the bottom, this is going to be on the right. So CH3, CH3 at the bottom, H on the left, and then the back carbon is the CH3 up top, H, H. And then you could do the same sort of analysis. And there are practice problem questions at both end of chapter and on the problem set where you do this, and I'll have you do this type of analysis on the quiz and exam. All right, well, that was a bit of a long lecture. I think I broke my lecture video record there, unfortunately. So I apologize for going a bit over 40 minutes. But until next time then, stay safe out there. Bye now.